Hello, welcome to another episode of learning how to repair power supply switching. Alright, in this session we want to explain the VSP circuit and why it needs to have power even when it is turned off. So let's get started. In order to be able to turn on a device that is initially off, there must be an initial voltage in the circuit that allows us to start the circuit. This is the reason for the presence of a standby voltage. Before the entire power is turned on, there must be a voltage that eventually reaches the motherboard. That's why on the motherboard, before the computer is completely turned on, we have a voltage of approximately 5 volts. When you press the power button on the computer case using the standby voltage, the startup operation and a command are sent to the IC inside the power supply. The power supply IC, which is related to the control circuitry that we will become more familiar with in the later sessions, starts the power startup operation. The power supply turns on and connects the other output voltage such as 12 volts, 5 volts or 3 volts, and as a result the motherboard turns on. That's why the standby circuit must have voltage before we connect the power to it. First of all, you need to familiarize yourself with the main components of the standby circuit. These are the key components involved in the operation of the standby circuit, and if any of them become faulty, causing the standby circuit to the malfunction, such as not having voltage, you need to identify these components and test them. I will introduce these components to you. The first component is the FET or MOSFET transistor, which is located in the first heatsink. From the input side of the circuit where large capacitors are placed, there is the first heatsink. This transistor is related to the standby circuit and needs to be tested. Transistor testing is done by removing the transistor from the circuit and testing to see if it is functional or not. If it is not functional, we replace the transistor and put the same transistor number in its place. If it is functional, we can use it again. Before the transistor, there is a fuse resistor. This resistor functions like a fuse. In other words, if the MOSFET transistor burns out and draws excessive current, this resistor will burn out and cut off the power, preventing further damage to the power supply. That's the purpose of this resistor. Therefore, we also test this resistor. This resistor usually has a very low resistance, ranging from 1 to 2.5 ohms. If you test this resistor with the multimeter and find its value to be around 1 ohm or 1 ohms or at most 2.5 ohms, then the resistor is in good condition. After these components, there is a BJT, which is 90% of case in numbered C945. This resistor is closely related to the MOSFET transistor. This transistor is responsible for turning the power on and off for the MOSFET transistor. Keep in mind that we will have a practical test and analysis of the VSP circuit in the next session. The next important component is the optocoupler. This component is used for insulating the circuit. I will also explain how to test this component. The next component is the transformer. If you have tested all the components and replaced them, if they were faulty or found them to be in good condition, and you still observe that the standby circuit is not working, then you may suspect the transformer and you need to test the transformer itself. I will teach you the method of testing the input and output impedance of the transformer to determine whether it is faulty or functioning properly. However, I must emphasize again that in order to repair switching power supply, you need to have knowledge of electronics and be familiar with the components and how to test them. In the VSP circuit, we have a MOSFET transistor. There is a resistor placed before the MOSFET transistor acting as a fuse. There is also a small transistor here, usually of BJT type and commonly numbered C945. As mentioned, when 300 volts enters this transistor, the output of this transistor will be 50 volts, which goes towards the transformer and is supposed to be connected to the transformer. The problem here is that the transformer doesn't work with DC voltage. The solution to be able to convert the voltage into AC is to use a smaller transistor of the BJT type. This type of transistors have a very fast switching capability and perform this task quickly. So we use this transistor and we connect the output of this C945 transistor to the input or the gate of the MOSFET transistor. Because if we continuously switch the voltage at the gate terminal, the output voltage from the MOSFET transistor will also have a switching behavior. However, please note that the C945 transistor number may vary in some power supplies. If it has a different number and the transistor is faulty, you should definitely replace it with an equivalent number. But in most power supplies, especially green power supplies, the C945 transistor is used. So they connected the output of the BJT transistor to the gate input of the MOSFET transistor, and when the transistor switches rapidly between on and off states, it provides a pseudo AC voltage in a switching manner. The important point here is that also this voltage is being switched on and off and is not smooth continuous DC voltage. It still doesn't qualify as a true AC voltage, and that's why the transformer cannot work with it. What's the solution? In order to convert this voltage into a sinusoidal waveform, which is the true AC voltage, they have used a capacitor aligned with a very low resistance. This combination is placed in the circuit. In this configuration, the final output is in the form of AC or sinusoidal waveform, which the transformer can work with. But how does the capacitor function in this case? The capacitor stores the electric charge and the resistance limits the current intensity. It's important to note that the resistance and the capacitor are connected in parallel, and in this configuration, the resistance consumes this electric charge. So in addition to the voltage being switched on and off from transistor, it enters the capacitor. What happens here is that the capacitor stores the electric charge and the resistance consumes it. Then the capacitor stores the electric charge again and the cycle continues, which is why the output becomes a sinusoidal waveform. For example, AC in this way. AC electricity is generated and the transformer can utilize this electricity. In summary, electricity enters a MOSFET transistor and the output of the MOSFET transistor is switched on and off by a BJT transistor. Through a simple circuit consisting of a capacitor and a resistor, the electricity is converted into AC form. Finally, it enters the transformer and passes through it. This is the point where we can test the transformer if it's malfunctioning. The order of testing the components is as follows. First, we test the fuse resistor. Then we test the MOSFET transistor followed by the BJT transistor. We also test the capacitor and the resistor, because if the BJT transistor is faulty, it can cause excessive current to follow through the resistor, ultimately damaging the capacitor or the resistor. Before checking the transformer for its functionality, there is a very important component that must be tested. That component is called an optocoupler or photocoupler, and I will explain its purpose, testing method, and schematic to you. An optocoupler is a crucial component that allows us to connect two sections of a circuit in an insulated manner. We mentioned that the power circuit is divided into two primary and secondary sections that are connected and insulated from each other using transformers. To establish electrical communication between these two circuit sections without physical connection, we use an optocoupler. The functional representation of an optocoupler is as follows. An optocoupler is a combination of a transistor and a diode. The diode used here is a regular LED, and a regular transistor is also included, with the difference that the transistor in this case has a collector and an emitter, which you can observe the pins for. In the optocoupler, there are two pins related to the LED and two pins related to the transistor. The operation of an optocoupler is as follows. When we wanna turn on the transistor inside it, instead of using voltage to activate the base of the transistor and establish a connection between the collector and emitter, the base of this transistor is stimulated by light. This causes the transistor to allow current to flow from the collector to the emitter. So essentially, an optocoupler is a combination of a light emitting diode or LED and a transistor, where the transistor itself operates using light. When the light of the LED is interrupted, the connection between transistors pins is also interrupted. The difference that an optocoupler has compared to normal operation is that as the intensity of the LED light increases, the current or even the voltage that the transistor can allow to pass through itself changes. In other words, with increasing light intensity, the current passing through the transistor inside the optocoupler also increases. And as the intensity of the LED light decreases, it ultimately reduces the current received by the base pin, which reacts to the light. In this way, we can establish isolated electrical connections between different parts of the power circuit without the need for physical contact. Why do we use optocouplers in switching power supplies? The main purpose of an optocoupler is to ensure that the voltage coming out of the power supply is fully stabilized and does not fluctuate. In our computer power supply, for example, we typically have outputs of 12 volts, 5 volts, and 3.3 volts. The 5 volts voltage, for instance, should not become, for example, 6 volts, and the 12 volts voltage should not become, for example, 13 volts. So to stabilize this voltage, there is a controller IC in the circuit that monitors this output voltage and prevents them from exceeding or falling below the desired levels. This voltage monitoring is actually carried out by a circuit called overvoltage protection, which is connected to the optocoupler, and the optocoupler sends information to the primary circuit. Now the operation of the optocoupler is as follows. For example, when the 12 volts power voltage becomes a 13 volt, the overvoltage protection circuit detects it and sends information to the optocoupler. The optocoupler then precisely communicates the increase to the primary circuit, which realizes that there is an increase in the output voltage. So what does it do? It slightly decreases the voltage by changing its frequency to stabilize the voltage and prevent it from exceeding a certain threshold. Conversely, if the voltage is below the normal range, the overvoltage protection circuit again sends information to the optocoupler, which relays the information to the primary circuit. The primary circuit increases the voltage to bring it back to the normal level. All of these actions happen instantly. In this way, the optocoupler and the overall voltage protection circuit constantly report the voltage output to the primary circuit. In this situation, if the primary circuit fails to recognize the voltage output, it will cause the standby circuit to malfunction and shut down. If the optocoupler malfunctions during this process without any issues in the output voltage, the primary and secondary circuit will have no communication. Since the primary circuit doesn't receive any information, the power supply remains off. That's why testing the optocoupler is crucial and must be done. In the next session, a practical explanation of how to test the optocoupler will be provided. So until the next session, if you have any questions, please be sure to ask in the comments section. Thank you for liking this video and don't forget to hit the subscribe button and the bell icon next to it. So take care until the next video.